Hello everyone, and welcome back to physics-based animation. In the last video, we learned how to formulate the equations of motion for an elastic object using the finite element method. In this video, we are going to tie up some loose ends from last time, including how to more robustly integrate our finite element systems in time in order to create physics-based animations. Remember, the previous video ended with us once again deriving the equations of motion for our finite element system. And they take on what should now be a familiar form, with a mass matrix on the left multiplying the generalized acceleration and the generalized forces on the right. If this looks unfamiliar to you, best to review the previous few videos just to make sure you have this at your fingertips. And you can find links to those videos in the description below. If you cast your mind back to the third video in this series, you might recall that we introduced a relatively simple time integration scheme to somewhat stably simulate mass spring systems. We called this integrator the linearly-implicit time integration scheme because while it started life as a Backward-Euler integrator, we used a first-order or linear approximation to arrive at an efficient simplification. And actually, this works quite well if we carefully choose the parameters, time step, and stiffness parameter for our finite element simulation. And here we can wiggle this bunny pretty happily, and everything seems to be going just fine. However, because our integrator is only a linear approximation of the real thing, we can also easily construct examples for which it will fail. This armadillo is smaller and stiffer than our bunny, not unreasonably so, but we see that even when undergoing similar deformations, these changes to the simulation setup cause catastrophic failure. In order to spare armadillos everywhere, our linearly implicit integrator will have to go, leaving in its place the full Backward-Euler update. This will lead to much happier armadillos everywhere. We've been looking at the Backward-Euler update as being comprised of a velocity equation and a position update. Now, if we substitute the position update into the velocity update and set the resulting equation to 0, we see that we can find our updated generalized velocity, q dot at t plus 1, by solving a nonlinear root finding problem. Now that's a bit of a shame, since nonlinear root finding is, in general, very difficult. However, maybe there's an equivalent but easier problem we can solve to get the same result. Fortunately, many root finding problems can be expressed as optimization problems, and this is helpful because there are a wealth of well-understood algorithms for performing optimizations. To see this, let's take a look at a generic minimization problem, where we are trying to find the optimal value of some variable y, which returns the smallest value of some energy or cost function denoted by E. Optimization theory tells us that the gradient of our cost function with respect to the parameters is equal to 0 when evaluated at this optimal solution. Our gradient is nothing more than a function of which we are trying to find a root, and this establishes a relationship between minimizing a particular objective and solving a particular root finding problem. Let's have another look at our Backward-Euler update equations. Our goal is to build an energy function E for which the gradient is our Backward-Euler velocity update. If we can do this, we can solve an optimization problem rather than a root finding problem. So let's see if we can draw a line, or several lines, between our update equations and some scalar energy function. Alright, here's our Backward-Euler velocity update equation with a minor change made. We've replaced the variable q dot at t plus 1 with the variable v. That's because q dot at t plus 1 is going to be the solution to our optimization problem. V will just be the velocity variable we search over. Let's make a few preliminary observations about our update equation. We can immediately see that it's made up of two pieces. The first piece is kind of simple. It's linear in our velocity, v. The second piece looks a bit trickier until we recall the relationship between generalized forces and potential energy. Further, revisiting our position update equation reveals that delta t is just the derivative of our generalized coordinate q with respect to the velocity. This is really nice because we see that this second term is really just a chain rule of the potential energy. In other words, it's just the gradient of the potential energy with respect to our velocity variable v. Now we just have to integrate both terms of the equation. Integrating our linear first term readily produces a quadratic function of v, and integrating our second term recovers the potential energy, and this comes from the fundamental theorem of calculus. Now, armed with this energy function, we can re-express finding an appropriate Backward-Euler velocity update as minimizing this new energy. Here our optimal velocities, v star, are our generalized velocities, our q dots at time t plus 1. Typically, we will have some initial guess for v, and now our goal is to find a way to get from that initial guess to a local minimum of this energy function. There are many ways to solve such optimization problems, but primarily we are interested in a class of algorithms called gradient-based optimization schemes. These algorithms all share a common set of stages. In step 1, we supply the algorithm with an initial guess for the optimal velocity value. Now normally we set this initial guess to 0, or the velocity from the previous time step. Next, we check if our initial guess is the answer. A standard way to do this is by looking at the norm of the gradient of the energy function. If this is close to 0, determined by a user-supplied tolerance, we stop the algorithm as we've solved the problem. If our guess is not the answer, we pick a direction in which to look for a better answer. And choosing this direction is a major way in which gradient-based optimization schemes differentiate themselves. So we'll skip this for now and circle back later. Finally, we use our search direction to update our current guess. Normally we do this by adding some proportion of the search direction to this guess. In optimization, we call this proportionality constant, here denoted by alpha, the step size, though it gets different names in different fields. Gradient-based optimization algorithms iteratively build a path between our initial guess and a local minimum of our cost function. The path that gets built depends on the exact nature of the algorithm. To make this more concrete, let's look at arguably the most famous gradient-based optimization scheme, gradient descent. Gradient descent chooses the search direction to be the negative gradient of the energy function, evaluated at our current guess. This makes a good deal of sense since locally the negative gradient points in the direction of maximum decrease of the energy function. It's the direction we would travel if we wanted to reduce the cost function the fastest, but only locally. Let's take a look at how gradient descent behaves on a famous test energy function, the Rosenbrock function. This cost function, or energy function, has a minimum value of 0 at the point 1, 1, the lower right-hand corner. If we think of this function as a landscape, we can see that this minimum is nestled at the end of a long, narrow valley. Let's see what gradient descent does on this example. We start by computing the gradient at our initial guess, and we take a step. Remember, this search direction is locally the best thing we can do. We repeat this procedure again, and notice that something funny is happening. These two steps have oscillated between the energy function's valley walls. In fact, this behavior will continue until we reach our minimum value. Why does this happen? Well, the gradient, our search direction, is only locally optimal. It doesn't take into account any neighboring information. While the best instantaneous move to reduce the cost might be to go straight down the energy function valley walls, in the long term, a better choice would be to walk along the flatter valley floor. And the next algorithm we examine will try to do just that. That algorithm is Newton's method, the workhorse gradient-based optimization algorithm for many applications, including physics-based animation. The major difference between Newton's method and gradient descent is how the search direction is computed. In order to compute the search direction, Newton's method will build a local quadratic or bowl-shaped approximation of the energy function. And it will choose the next point in its path by minimizing this quadratic approximation. Doing this repeatedly will construct a path to our local minimum, but a different path than gradient descent. This is because our quadratic approximation takes into account not just the local steepness of the energy function, but also its curvature. For many problems, this results in faster convergence to a solution, especially if we start with a good initial guess. Here's the pseudocode for Newton's method. Note that the only difference between it and gradient descent is that the search direction will be chosen by solving an intermediate optimization problem. Offhand, this seems like a lot of complexity to add to our optimization scheme, but we'll see shortly that it really isn't that bad. To see how this works, let's return to our generic optimization problem. In the vanilla version of this problem, we search over our variable y to find a minimum. However, let's say we already have a guess at the answer yi. We can instead ask, is there a small offset to this guess, d tilde, that minimizes our energy? Now, we still can't solve the whole optimization problem, but we don't really need to. We just need to make some progress towards the answer. To get a reasonably good update, we can perform a second-order Taylor expansion of our energy, and this gives us a quadratic energy we can minimize to get a guess for our search direction, d. In order to build this quadratic approximation, we need to compute the gradient of our function and the matrix of second derivatives, the so-called Hessian. You might think we also need our cost function value at yi. However, because this term doesn't depend on d tilde, we can safely exclude it. Plugging this back into our Newton's method algorithm makes things look a little better, but we still need an efficient way to minimize this quadratic function. Fortunately, minimizing quadratic functions is not too difficult. Alright, here's our quadratic function, and we can find a minimum by searching for d tilde such that the gradient of the function is 0. Because this function is quadratic, the gradient is linear, meaning that we can compute our search direction by solving a single linear system, which involves the local Hessian and gradient of the energy function. Now we see the basic Newton's method take shape. We choose the search direction by solving a linear system, and now the final piece of the puzzle is the computation of our Hessian h and our gradient g. And we can arrive at formulas for these values by differentiating our Backward-Euler energy function. Computing an initial set of derivatives gives us the gradient of the function where we see the appearance of the negative generalized forces. A second differentiation yields the Hessian, which is composed of the mass matrix and a negative stiffness matrix. Good news for us, we've already seen how to construct all of these terms in previous videos, both for mass spring systems and for finite element systems. You should be feeling a little bit of deja vu at this point, because these terms are very similar to the ones we use to compute our linearly implicit Backward-Euler update. However, here we reevaluate our gradients and Hessians using our current velocity guess during the optimization procedure. And now we have all the pieces to implement basic Newton's method for backward-Euler integration. We can code this up and run it, and, well, unfortunately, it will still break sometimes. Given the amount of work we've done, that's pretty disappointing. But let's see if we can figure out what's going on here. When I was describing Newton's method, I drew this suspiciously perfect picture of its operation. Well, you were right to be suspicious, as I was ignoring something worrying. The energy of our new point computed by following the Newton search direction d may actually go up. That's because our search direction is computed using a quadratic approximation to the real energy function, and it may still be inaccurate. If we aren't careful, we can spiral away from the local minimum, and this can lead to problems. In these cases, the point we actually want to move to is somewhere between our start point and our computed next step. Fortunately, a small modification to the basic Newton algorithm is going to allow us to handle these cases. While there are several ways to address this problem, we will use a fairly straightforward one. Rather than always take the full Newton step, as dictated by our step size alpha, we will instead scale alpha at each iteration to ensure that we are always minimizing our function. The process of picking a good alpha is called a line search, and it's a separate little algorithm that we insert between computing our search direction and updating our velocity estimate. To see how this works, let's go back again to our generic optimization problem. There's an important observation to be made here, and that is that once we compute d, selecting an optimal alpha can be considered a one-dimensional optimization problem, and this can be solved with 1D search fairly efficiently. We can get a better feel for this by noting that in our previous example, the desired yellow point lies on the line between our current guess and our vanilla Newton step. Because of this, we can make our lives easier by examining this problem in one dimension. Here's a one-dimensional view of our energy function along the search direction d. Here we see that our updated velocity, computed with a default alpha, actually produces a higher energy than our initial guess. We want to prevent this from happening, and so we need to pick some criteria which determines whether an update is acceptable or not. Our criteria will be sufficient decrease, that our updates must always make progress towards a solution. Here we can define a decreasing linear approximation to our energy. The slope of this threshold is controlled by the user parameter c, and will accept any update that falls below this threshold. We can search for acceptable updates by scaling alpha using a user-defined parameter p. If p is less than 1, then repeated multiplications will pull our updates back towards the initial guess, meaning we should be able to find an acceptable update that has a lower energy than our initial guess. This will occur unless we are already at a local minimum of the energy function. Here we take advantage of the fact that we don't have to find the absolute minimum during this 1D search. Rather, we just have to ensure we keep making progress towards it. This will help ensure that after some finite number of Newton iterations, we will arrive at a local minimum. We can codify this 1D search as a relatively simple algorithm called backtracking line search, so named because we start by assuming a large value of alpha and then backtracking to find a value that yields sufficient decrease in the cost function. We terminate the search once we find such a value, or if alpha becomes imperceptibly small. This means that the algorithm is stuck and has done the best it can. Okay, let's see if line search has made any difference at all to our results. What we find is that line search cleans up all the stability issues we were experiencing, which means we've finally seen all the pieces we need to implement a pretty good version of the full Backward-Euler time integration scheme. A reminder that just because we focused on finite element systems in this video, these techniques are readily applicable to the simulation of almost any physical system. Now that we finished up talking about time integration, we're going to switch gears and talk a bit about how we can make some of these now stable simulations a little bit more visually appealing. You may have noticed that we typically use very low resolution meshes for simulation. That's because our simulation meshes are often volumetric. There's many vertices hidden inside this bunny that don't affect its outward appearance. We often also have available to us a high-resolution surface mesh represented as a triangle mesh. Wouldn't it be great if we could somehow combine these two representations? We could compute the simulated motion using our tetrahedral mesh, but display the motion using our higher fidelity surface mesh. Well, finite elements are going to make that very easy. One of the key parts of the finite element construction was that for any point inside a finite element tetrahedron, we could rebuild its position in the world space using our shape functions, here denoted by phi0, phi1, phi2, and phi3. We can exploit this mapping to stitch our simulation and surface meshes together. We call this stitching skinning because our surface mesh is used as an outer skin for our simulation mesh. Let's zoom in on a single simulation tetrahedron to see how this works. Now, it's going to be easier to diagram this out in 2 dimensions, but never lose sight of the fact that our yellow triangle here is really standing in for a tetrahedron. It has 4 vertex positions, and we can express the world space position of every point inside the tetrahedron using our shape functions. Let's take a look at 3 points from our high-resolution surface mesh, capital XA, capital XB, and capital XC. These points happen to fall inside this particular tetrahedron. From our shape function equation, we immediately know that the world space position of these points can be computed from the positions of our tetrahedral vertices. And we do this by evaluating the shape functions at each surface vertex position. Remember, these positions are all in the undeformed space, so this can all be done as a pre-process, once both the simulation and surface meshes are loaded. Looking at these equations, we see that the world space positions of our surface mesh are linear in the positions of the tetrahedron vertices. This means we can rewrite this set of equations using a matrix vector product, where W is a matrix of skinning weights, in this case filled with our shape function values. While the previous image showed the weight matrix for a single tetrahedron, we can of course construct a similar matrix for our whole bunny. This requires finding the tetrahedron that contains each point of our surface triangle mesh, but remember, we only need to do this once at startup time. Once we have this relationship, we simply fill in W using the appropriate shape function values. Note that W will be a very sparse matrix because each surface mesh only needs information from 4 simulation vertices to compute its updated position. Once we have constructed our sparse W, we can use it to animate our surface mesh via a single matrix multiplication performed at each time step of our simulation. And here's what that looks like. We can start by visualizing the motion on the simulation tetrahedral mesh. But once we turn on skinning, we can transfer this motion to our high-resolution surface mesh. Don't be fooled. The motion of our armadillo is always generated by the simulation mesh. but we can map that motion onto the high-res mesh using our W matrix. And with this, we've finally seen everything we need to create a robust, visually appealing finite element simulation. The combination of techniques presented in the last two lectures really forms the core of much of modern physics-based animation. So it's a good idea to watch this video a few times to make sure you've already got everything down pat. Next video, things are going to get even more interesting as we move away from volumetric objects and see how we can apply all the things we've learned to the simulation of cloth. We'll also make our first foray into handling collisions, so lots of good stuff coming up. Once again, thanks for watching, and hopefully I'll see you back next time.